Okay, now I have two experiments. What we have, one, I'll take the string whose Young's modulus have to be determined. Okay, there's a string whose Young's modulus have to be determined, and that I'll show it here. So two set of experiments what we have. Another red color. This one red color will show it. Okay, we have to calculate the Young's modulus of a wire. So what shall I do? So let's go back to the how you define Young's modulus. Young's modulus equal to stress by strain. What is the T? T should be equal to mg. T should be equal to mg. So therefore this y is equal to, so this mg by a further. Already I think it is written. What is x? X is the elongation. So let me use the same symbols. X, and this is the length L naught. Okay, no, already the first diagram is, why I'm bringing this diagram is what something we are supposed to think and analyze. Okay, let's okay, now what you can do here. So actually, if you go to the lab and start doing this elongation one, so you try to do this experiment. This will be mg by a, y equal to, this will be elongation x by L naught. Now, so what I do is like, as I, so this will become, what is T? T is equal to, in fact, mg. Now you try to say this. X by L naught. So what is X? X is elongation. So how do I measure? So that I'll take a scale. So as I keep on increase the load, L naught will be a constant. L naught is the initial length of the wire. Young's modulus, this area of cross section. So as I increase the load, the elongation starts increasing. The elongation starts increasing here. So now I'll rewrite the formula. X equal to L naught. I think this equation 1 by y, no? It is 1 by y. This one, what is A? A is the area of cross section. So I think I'll rewrite all the things. It'll be easy. No. So x equal to mg L naught by pi y r square. Okay, let's get into the discussion. So now L naught is initial length, Y is Young's modulus, pi, R is the radius. These are constant, no? So what things will be here? The M, better select A. As we increase the load, the elongation will start increasing. As we increase the load, the elongation will start increasing. Then as we increase the load, the elongation will increase. So let me plot that elongation versus the load. What is this mg? Mg I'm going to call load. So I'm going to keep on increase. So practically here how the situation will be, the situation there's a rough diagram it is given. So in the lab, no, usually it will be of like this. There's an angle. Here there'll be a pan, and here I'm going to put a load, and this is L naught, initial length, without any load. So as I increase the load, so there will be an elongation. Okay, come for this one. As I keep on increase the load, the elongation, the string will increase. So this is X, you can put it. Yeah. No, as I increase the load, the elongation, the string will increase. So X equal to L naught Y by T by A. So T is equal to what? Mg, this one. Now what is a, here what happened? I'll measure the elongation versus the load. So I got the X by Mg graph. Then Young's modulus is what needed. So what is Young's modulus here? So X by L naught is what? Like a X by Mg is what I can calculate from the slope. So I needed this particular Young's modulus. So further, if I rewrite, now you see this one. So this can I calculate from the slope? Yes, it is slope from the, and this is this part is a constant. So from the slope, what when I'll get reciprocal of slope will be mg by x. I'll substitute that value. Then what when I'll get the Young's modulus. I know L naught and pi square. This is a one elementary method in self-installing. Why we are not preferring this? And I'm saying that this is what the experiment. This we don't prefer. Anybody? This will be more troublesome question for you. Why do I'll go for this? Tension will not be constant. Okay, that is not the situation. Okay, we'll need not to bother about that. Anybody? What is the drawback of this? See, what is the drawback of this will be? So what is the drawback of this one will be? Means as you what is the drawback of this one is like as we increase the load, the elongation will increase. No doubt that one. Any temperature changes, even that will also be reflected. No, am I right? Any temperature changes, so there'll be due to change in temperature, there'll be elongation, and the elongation due to thermal expansion also will come. But what is this X we are defining? This X we are defining is elongation due to load. But what we measure? But practical open, there'll be elongation due to temperature also. Are we including that? It is not included here. So what is this? This elongation, what we are measuring is due to load and also due to temperature. Due to load and also due to temperature. So therefore some error is there. So what we are, this formula is meant only the elongation due to load. But what if we have this elongation is due to load as well as thermal expansion. But in our formula, we should have the elongation only due to this. So can I measure elongation only due to load? Not possible, because you know initial length and you calculate final length. The difference of that is what? The elongation. So there what happened, the elongation due to thermal expansion is also introduced, and that is not included in the formula. So definitely there'll be error. Are you getting now? So what is the drawback of this formula? First method, the elongation due to thermal expansion is not accounted. The elongation due to thermal expansion is not accounted. The elongation due to thermal expansion is not accounted formula, or the formula is only elongation due to load. The thermal expansion, the elongation due to thermal expansion is not included here. So definitely it's been error. So I'll write the comment here. X is elongation due to load and also ambient temperature we call, or the surrounding temperatures also due to surrounding temperature. X is elongation due to load and also due to the X is elongation, this one. So this elongation is not included. That's why this is having some error. So therefore the what we get value will not be correct. This is the main reason why we go for Young's Searles double bar apparatus. Such things will definitely will trouble you a lot in exam, because this is not like something where uh, you can derive or you can analyze. It's a laboratory information. It's a practical information where student must be known in exam. So you can't think all such things in exam, because first of all, you are not seen this apparatus, not possible. So therefore, I suggest you like gathering information regarding the experiments is the best thing. Write down all the set of points, keep it ready. Anything related to that only they should ask. But in formula, what will happen? X is total, X is total this one. But here what happened? We are reflecting only elongation due to load. So there is some error. Let me put it here. Temperature, but we have substituting only, but the formula is designed due to load only. Okay, there is a drawback. Okay, got this one. Now I'll go for, so in a simplest way, shall I say that the effect of temperature is not considered in this particular formula. Why to all this one? Okay, now we'll get into this one. So the effect of temperature will be taken care using Young's Searles double bar apparatus. So there's a reference wire. Both the wires are identical. Both will have same length. Both will have same area of cross section. Both are made up of same material. So I'll connect here. So there's the experimental wire and there's a reference wire. Now what we do is like, so here there's a thing. So there's the experimental wire. Whose Young's modulus I have to determine, but both are identical. I'm telling this one. That's what it's telling. So we have here spirit level. Somebody. We have here a spirit level. So what I do is like, so using the spirit level, so I can do adjustment. So first what happen? The weight W is what I'm going to increase here. So or this is like a normal, there's a spirit level. So here is, all of you have spirit level idea. I'll do one thing, only that yeah, no. Hook H1 carries constant weight. So there's a constant weight. I'm showing it. And there's a, I think we have some around 21 experiments are there. Huh? Mains come advance. So all the 21 experiments we are supposed to learn. I don't know how much of time we have. That's why I just directly started the discussion today. We have plenty of, this 2 weeks will be very, you can say, crushed one. A lot of things we have to go through, and we have to go for the mains grand test. And from student side also, I want you to recollect as much as possible content, especially the difference in syllabus, no? So this week and next week. So plenty of things are to be read and memorized here. Time will not be sufficient. I'll try to maximum cover almost everything. Let me try. If possible, let me take extra class. What is there in that one? Okay, there's a standard weight, constant weight. This one, I'll suspend it. No, initially. So if I suspend it, definitely open the spirit level will be initially will be leveled. So then it will tilt like this, no? So for that to happen, I will rotate this screw here. So by rotating this screw, what will happen? I'll bring that level, the drop exactly the middle of that one. You must have a background of what is the spirit level. I think, where do we use anybody spirit level? I want some answer from your side. Let's see. Okay, construction sites, whether it's a horizontal or not, this one. So this everything will be water, no? This everything will be water drop. This, and there'll be a small bubble will be located. Very important device it is. Okay, this one. So there's a water. There's a drop. So there's a air drop or bubble, you write. If the bubble exactly, and they'll give that marking will be made available. Red color not possible. Red color marking will be there. So if the air bubble is exactly between this one, so definitely what happen, it is horizontal. If you tilt it, it will move in this direction. If you tilt like this, the bubble will be here. To say that exactly this particular surface is horizontal, if the bubble lies within that marking, no, so then it's said to be horizontal. The similar situation here. So when you hang this weight, so this part will move down, no? So the red color wire will have more length. This will have more length, and what we have is this was the thing. So how the spirit level will adjust itself like this. Am I right? So and the bubble, this particular bubble, what happened will come here. I can't draw that yellow blue color, only yellow I'll show it. The bubble will be here. So what does it mean? This having more elongation because by hanging this weight H1, it is a fixed weight. Hang that after hung that particular weight, so this will get elongated. So this is the elongation. Now to make it level, what happen? I will rotate this screw. By rotating this screw, what happen? You are pulling this particular frame. This F1, F2 are called as the frames. That one. So by rotating this screw like this, so this particular screw, what happen, will be connected to screw level, the spirit level, this one. So as you rotate this screw, this particular entire frame will move down so that it will be the spirit level will come like this. Okay, getting this one, the spirit level will come like this. So this is the elongation it has suffered. So like this, what happened? How to elongate this particular wire? How to elongate this particular wire? By rotating this screw. How to elongate this particular thing? By rotating this particular screw. That's the thing. So now okay, I am in a better position. So I'm going to increase the weight here. So as I increase the weight here, let me see. Wire being an experimental. Okay, H2. So here what happen? I'll keep on increase the load. As I increase the load, so definitely what will happen to this? This particular frame is going to move down. So as I increase the load, so this particular frame what happen will move down. So this will get elongated. Now to measure how much of this elongation, so what I do is like I'll rotate the screw here. I think he has shown the wrong way. I will the diagram little bit changes. Huh? Some. Some correction is there in the diagram. Yeah. Okay, no. So there's a screw. I'm going to rotate this screw here. Now you see this. As I know what will happen. How much elongation, how to measure? We can't measure by scale or something. I will rotate this particular screw. I'll rotate in such a way that till this bubble, as I rotate it, till this bubble, what will happen will come. So now this is the initial setting. Okay, afterwards, finally, what will happen is as I increase the load here, this will elongate it. So it will get tilted. The system, what happen, will be tilted. I will take it out this. This is not needed. You'll get confused. Now, why do length of this will increase? Because we are increasing the load here. This will get elongated. How to measure this elongation? You can't take scalar. It will be very small of order micrometer. How to measure that elongation? So I have a screw here. So as I rotate this screw, it's called a micrometer. As I rotate it, so as I rotate it, what happens? This particular frame F1 will be pulled down. As it is pulled down, So that this will start getting elongated. So how much I should elongate, how much this got elongated due to suspension of weight, it should get elongated. So how do I come to know that the level will help us here? So as I rotate this screw, so this particular red color experimental, there's a reference file will also get elongated. How much it should get elongated, so that how much this got elongated. How do I come to know? When the bubble comes to this position. So here is what we'll be noting down the reading. So you come to know from the reading what happened, you come to know what is that elongation. So for a corresponding load, what happened, we got elongation. Again, what I do, again, it has come level. So it got elongated. There's the initial first elongation. Got the idea, no? Next, again, what I do, I'll increase the load. Then further, again, it'll get tilted and the bubble will shift like this. The bubble, actually, it should come on this side, no? Okay, the bubble will get shift. So again, what will happen, what I should do, I should rotate the screw in such a way that this will get elongated. And how long I should rotate the screw till the bubble comes and aligns at the midpoint of the spirit level. So like that, for every increasing load, what happen, I'll note down the elongation. So this got elongated. How to measure this elongation? I'm taking help of this spirit level. So like that, what I do is like I'm going to plot the elongation versus the load. And what is our formula? Young's modulus equal to, so the elongation x mg. So from here I'll get a slope. So what I do is like the load, the graph will be, so we wanted this mg, this is elongation. Okay, fine. Now this is the, so calculating the slope of this this particular thing, will what we get is tan theta. For different values of load, I'll calculate the elongation. How to calculate the elongation? The spirometer is what I'll be taking help of, the spirometer. From that, I'm going to note down. Or say micrometer, what all you can call. I think if you go for lab, no, it'll be much easier. So it's a micrometer, nothing but again a screw gauge only in circular form. Don't think again something very big. Now you can ask questions, sir. What was the wrong with the first method? Why you did? So now, any like a due to temperature fluctuations, if this rod elongates, even this will also elongate, no? And what all we note down readings will be only due to suspended load, added load. Are you getting the trick here? Now, suppose by chance temperature increases, how much this will elongate, that much this will also elongate. So what we did now, using the Searles double bar apparatus, the effect of temperature is what nullified. Getting the trick? Previous problem, not like that. You can't do anything with this elongation due to variation in temperature. After bubble gets displaced, I'm going to rotate this micrometer so that the spirit level will become horizontal. What shall I do? I'm going to rotate micrometer so that this will get elongated. How much this wire got elongated, that much this should be elongated, no? Because I want to measure that elongation. So how to measure this elongation? This elongation. How to measure this elongation? For that, what happen? I'll make this wire to experiment, this reference wire to elongate. How much I should elongate till the bubble comes to the midpoint, the reference level, from here to here. Then I note down how much I rotated. Then from that, what happen? I'll come to know the elongation. As I say, for W1 we got X1. Next, I'll increase the load W2. Then again, the situation should be like this. Then again, what I do is like, again, I'll rotate this like a micrometer in such a way that the bubble will get aligned at the midpoint. Then I'm able to calculate the second elongation. Like that, what happen? We'll plot and we'll take a slope. We'll get the required answer. Got the idea? So what is a Searles double bar apparatus? The effect of the elongation due to temperature is nullified in this experiment. This is the main core idea. Can be asked for you in advanced exams, so you have to be very careful. Mains, advanced, anything that it be. He's saying something, no tolerance. Okay, you see this is something. What do you mean by that? The mass what I have, no, that is what, nothing but exact. What we have mass is, that is exact. What the mass, what we have is exact. If it is having any tolerance, what do you mean by tolerance? Because if the mass is given like this, m is equal to the load what we are going to add, if it is like this, what do you mean by this? There'll be some error in the measurement of mass also, that has to be included here. Usually we will not be, because the weights, what happen, we have a standardization, no? There won't be error. If by chance in exam, if they give like this, then you write delta m by m also here. Got the idea? So no tolerance in mass is telling. If there's a tolerance, means the mass will be expressed like this. The load what you're going to. So that's why in the Searles double bar apparatus, if the mass are standard, the formula will be like this. If the mass are not standard, standard sense like if they have some error, no, then plus or minus delta m by m has to be included. Got the idea? I'm going to go to the next experiment. There's a wire. So good theoretical questions they can ask you. Huh? So if they ask you something related to errors, okay, you know maths, but these things, unless you have read, not possible in exam. Note down reading of the reading of micrometer. After leveling the, what is that name is, can spirit level. They may ask you like, hey, when the reading should be taken, when the spirit level is not in level to the, when it is get leveled, or from leveled if it becomes not leveled. So this is a thing. So by increasing the load, so the experimental wire will get elongated, level will not be there, spirit level will not be at a level. Then by rotating the screw, so what happen, the spirit level will get leveled, and we are going to note down the micrometer reading that will be proportional to elongation of the wire. That's the idea. Any doubt? You please clarify.
Sir, effect of elongation due to temperature, how is it?
How much this wire will elongate, that much this will elongate. No, finish over. So what all we are taking reading now is only due to elongation due to load. No, that's what needed.
Are they both
Okay,
wires
sir.
of same material?
Same material. That's what standard wire. Both the wires should be of same material, identical wires. They should be identical. Strict condition.
Sir, if they're identical, then Young's modulus will be same, no, sir?
Let it be. Okay, no. What is the
So
problem?
what's the need of the experiment?
What happened?
We know the Young's modulus of the first one, no, sir. Both will be same, no, sir, Young's modulus.
We don't know Young's modulus of first one.
Actually, shall I tell you one thing? I don't know Young's modulus of wire. I'll take that wire. I'll cut into two parts. Same length, same area of cross section. I'll take aluminum wire.
Okay, sir.
I think we should have common sense now. Huh? Standard wire in the sense we know Young's modulus. We don't know Young's modulus of this and this. That's what we have to find out. What I do, I'll take a wire, I'll cut that into two identical parts, I'll suspend it. This will be really troublesome for students because it's the information, that's all. Until this teacher or you have not read information or teacher didn't share the information, not possible for you to crack such questions in exam. So anything theoretical questions that comes in exam,